base is the same. You see that you have this right here. It's the base, it's the same, and we're multiplying. What do we do to the exponents? We add them. Yeah. Multiplying with the same base. You keep the base and you add the exponents. That's it. Quotient rule. Quotient means divide. So if you're dividing two real numbers, right, and the base is the same, what do you do with the exponents? You subtract them. So it says dividing with the same base, you keep the base and subtract the exponents. Okay. Then we had a power to a power rule. When you have a power with an exponent outside, you take that power that's on the outside and you distribute it to the inside. And that's why I draw those arrows, because when I draw arrows, that means across the top, that means I'm multiplying, right? So I'm hoping that you guys are in the habit of seeing that arrow. So this just represents you're going to multiply, you're going to distribute that power. Okay. A quotient of a power says if you have a fraction or a quotient and it's raised to a power, that this gets distributed to the numerator and to the denominator. The power outside the parenthesis goes to both the numerator and the denominator. Then we had the product to a power rule that says if you have a product, like two numbers or two variable terms being multiplied together, and you raise those to a product, that, remember, we put what on each one of these terms? We put a power of 1 on them, right? And then we multiply this by them. So if you look at this xy, the quantity cubed, we actually would draw ones there, and then we take 3 times 1 to get x cubed, y cubed. So remember, if it does not have an exponent, we put a 1 there, right? That helps us remember to multiply everything by the power. Then we had negative exponents and zero exponents, negative and zero. Negative exponents, think about the bunk bed story, right? If you are sleeping in a bunk bed, right? So you're like laying in the bunk bed and your sibling is on the top bunk and they're like throwing a fit, and your mom's going to come in and like this person is crying and yelling and making all kinds of noise. Mom makes them move down to the bottom bunk. Remember that if you're in the top bunk and you have a negative exponent, I'm going to put a 2 down here. If it's like this, what do you do with that? You guys have to do what? I take this person from the top and I move them to the bottom. And once I move them to the bottom, they're happy. What do I put up here since there's nothing up there? A 1. I put a 1. Okay. 0, anything to the 0 power. Anything to the 0 power is 1, as long as it's not 0, because 0 is never equal to 1. Okay. So let's do some examples. So that's what we have here. We're just going to do some examples. So let's see. I'm going to kind of think about what I need to do. So I'm going to write off to the side. I know that I need to multiply the numbers. And I know that I need to add the exponents on the m's, because I'm multiplying those two m's together. So it might help your brain if we rewrite this. So I'm going to rewrite this as 2 times 2 times m squared times m cubed, because that's really what's happening. 2 times 2 is 4. And we just learned that if the base is the same and we're multiplying, we add the exponents. So what is my final answer? Yeah, 4m to the 5th. 4m to the 5th. Okay. So for our next one, I'm going to do the same thing. I'm going to multiply the numbers and add the exponents. So I really am going to rewrite it as 4 times 2 times r to the negative 3 times r squared. So 4 times 2 is 8. And r to the negative 3 plus 2 Well, what does that equal? Yeah, so I really have 8r to the negative 1. Can I leave a negative exponent? No. Which thing is being raised to the power of negative 1? Is it 8r that's being raised to the power of negative 1 or just r? Yeah, r is the only thing that's being raised to the negative power. So the 8 is positive. It's just 8 to the first power. It stays where it is, but the r is to a negative power. So we need to move it to the bottom bunk. So we can write it as r to the first power, but really I would just write it as 8 over r. Cannot leave negative exponents. That's mathematically gross. Can't have it. Okay. So for number 5, same thing. We're going to multiply the numbers and we're going to add the exponents together for the k's, right? So I really have 2 times 4 times k to the 4th times k. What if there's no power there? I'm going to put 1 there. So you see how I added a 1 to that k? 2 times 4 is 8. And k to the 4 plus 1 becomes 8k to the 5th. I'm going to put those in a little, I'm going to try to bubble in my answers. How do we feel about that? Are you guys okay with that? Okay. Let's look at number 7. We always multiply the constants together. So I definitely have to take the 2 times the 3. But what about the y squared and the x? Do I add those together? So what does it become? So are those the same base? Are y and x the same? No, they're not. They're not the same. So I don't use any rule on them. I just leave them the way they are. The only thing I'm going to do is arrange them in ABC order. So 2 times 3 is 6. And I'm going to have the x come first and the y squared come second. It doesn't have to, but we really always try to put our variables in ABC order. I know that sounds silly, but we try to. Okay. How are we feeling about these? Anything that you guys haven't seen? Anything that you don't remember? You feel okay with this? Okay. Let's look at number 9. So let's see. I have a 4 times a 3. Then I have a cubed times a to the negative 4 times b squared times b to the negative 3. So let's multiply the numbers first. 4 times 3 is 12. And then I have a to the 3 plus a negative 4 times b to the 2 plus a negative 3. So what is the exponent, Brian, that ends up on the a? What is the exponent that's going to end up on the a? So what is 3 plus negative 4? 3 plus negative 4. Yeah, good job. Negative 1. Okay. Gavin, what is the power or the exponent that's going to end up on the b term? Or what is 2 plus a negative 3? Yeah. So are we able to keep those like that? No. What do I have to do with those 2 negative exponents? This is all in the top, so I have to move them down. This is all in the top. So the 12 stays where it is, but these 2 negative Nellies, they go down to the bottom. Put them in the basement. They're being crabby. We don't want to deal with them. Move them downstairs. Right? It's like everybody has a crabby aunt, right? My Aunt Betty is always the one that, like, when we would get together for family reunions or Christmases or whatever, she just would She talks like that and she yells at you for everything you do, right? And so she was always the first person that we would like hope to go to the basement. God, I wish she would just go down to the basement, but she never did. Okay. What about number 11? Well, I know that if I have a power outside, I have to take it and multiply it by the power on the inside. So really I have x to the 2 times 0. So 2 times 0 is 0, and any non-zero number, anything that is not 0, raised to the power of 0 equals what? Look at your zero exponents rule on the other side. What does it say about zero exponents on the other side? It equals 1. So this is the same thing as 1. This equals 1. So number 13 is trying to trick you after doing number 11. Don't let it work. Don't let that happen to you. 13 is trying to trick you. So remember that this on the outside gets distributed to each power on the inside. So what should I do to the 4? Give it a 1. Yeah, this is 4 to the first power. What is going on? It's making shapes when I draw. And I don't want that. So 4 to the first power and r to the 0 power. So I'm going to multiply. So I really have 4 to the 1 times 4 power and r to the 0 times 4 power. So 4 to the, what is 1 times 4? So 4 to the 4th power. And what is r to the 0 times 4 power? 0. But 4 to the 4th is what number? Yeah, 256. Who said that? Was that you? Good job. 256. And r to the 0 is 1. So my final answer is just 256. So I'm going to let you guys do number 15. I'm going to let you do number 15. I'm going to freeze my screen. Number 15, you do. Perfect. To the power of 4. Okay. Anybody want to share their answer? Anybody? You want to share? No? Okay. Here's what I got. I got 81k to the 16th. 81k to the 16th. Because I took my 3 to the 4th power and I figured out what it was. 3 to the 4th power is 81. So 3 to the 4th power is 81. Okay. All right. I want you to pick three more questions on this page that we're going to do. 3 more questions on this page. I'll pick them. We're going to do 20 because that's a good one. And then we'll do 26 and 28. So let's do number 20. So number 20, I am going to rewrite this first as 3 to the first power m to the first power, because I want you to remember that if they don't have an exponent on them, they're raised to the power of 1. And then I'm going to put this -2 on the outside. So when you have a power being raised to a power, what do you do with this guy on the outside? What am I doing with it? Yeah, I'm going to distribute it to the powers on the inside. So it really becomes, let's see, 3 to the 1 times -2 is -2. And m to the 1 times -2 is -2. Can I keep those as negative exponents? No. So I'm going to draw a fraction bar. Whenever I have negative exponents, I'm going to draw a fraction bar. This guy is not happy in the top where he is, so I need to move him to the bottom. This guy is also not happy in the top where he is, so I need to move him to the bottom. But I don't have anything in the top. Put a 1. And I'm going to simplify that 3 squared because I know that 3 squared is 9. So I really have 1 over 9m squared. Okay. I'm going to jump to number 26, I think. Number 26. So there is a lot going on here, a lot of negative exponents. So when I see a problem like this, the first thing I do is do you guys remember what we did here when we saw something like this? We're going to move all the negative exponents right now. So is 2 happy where he is? Yeah, leave 2 where it is. Is x to the 4th happy where it is? Yes, leave that where it is. Is y to the -4th happy? No, I'm going to move it down to the bottom. And now it's going to become positive y to the 4th. Is z to the -3 happy? No, move it downstairs. Now it becomes z to the +3. What about the 3 in the basement? Is it happy? Yes, and I'm going to put it in the front. That's why I left some space there. What about the x squared? Is it happy? Yes, leave it where it is. What about this y to the -3 in the basement? Is it happy? No, so what do I need to do with it? Move it to the top bunk. What about the z in the bottom? Stays where it is. Okay. It is kind of. So now I'm going to use the rule that says I can't do anything with the 2 over 3. That's going to stay where it is. But I know that when I divide powers, if the base is the same, I subtract. If the base is the same, I subtract. So I really have x to the 4 minus 2, which equals what? X squared. Okay. If the base is the same, I subtract them. 3 minus 4 is going to give me a negative, right? So here's how we talked about this. You know that you have 3 y's in the top and you have 4 y's being multiplied together in the bottom. Where do you have more y's, in the top or in the bottom? Where's the biggest power? In the bottom. How much more? 1 more. So leave that y to the first in the bottom. So now we're done with that. The last one is this z. Both of them are in the bottom. If you're multiplying, you add the exponents. 3 plus 4 is 7. So your final answer is 2x squared over 3yz to the power of 7. Now you could do that problem 17 different ways. This was just the way that we created the least amount of errors, because we messed up when we had to minus a negative and all kinds of stuff. Okay, number 28. Number 28. So what are we moving? What's getting moved? Yeah, the only thing that's getting moved is this guy downstairs, right? I'm moving this down to the bottom. So I have 2, oh, sorry, I said 2 and I drew a 3. I have 2h cubed k to the 4th. And in the denominator, I have 3j to the first power times k times j to the third power, because I moved this down to the bottom. Okay, so can I simplify that 2 over 3? No, it becomes a repeating decimal, so I'm just going to leave it as a fraction. Is there any other h in the top or the bottom that I can combine this with? Any other power of h? No, so that stays just like it is, h cubed. Is there any other power of k? Well, yeah, there's a k to the first down here. So you have 4 powers of k in the top and 1 power in the bottom. Which one has more power, the top or the bottom? Top or bottom? How much more? 3 more. And then let's look at your j's. You have a j to the first and a j to the third. So that becomes j to the what power? 1 plus 3 is 4. Yeah. So I filled in all of the words on the next 2 pages because I wanted to be able to kind of zip through them. So these are all the rules for exponents. All of the rules for exponents. You got it, Peyton? Okay. So next we're going to talk about exponential functions. So the first thing that we talked about is exponential growth and decay. Exponential growth and decay. So we said that an exponential function, see, I already filled this in for you, is in the form y equals a times b to the power of x, where a is the initial value, also called the y-intercept. This is so important. Remember that this is the y-intercept, this right here. That tells you where you're going to cross the y-axis or where you're going to begin, okay? When we think about the domain and the range, the domain is all real numbers. We can use any real number for x. And then our range is going to be either all positive real numbers or all negative real numbers. And when we think about what happens to exponential functions, they either approach 0, approach positive infinity, or negative infinity. So here's what it looks like. Exponential growth happens when a, that first number, is greater than 0, and b is greater than 1. B is called your growth factor, right? It's the multiplier. So that 3 is going to be the one that's getting multiplied, raised to a power of x, because it's an exponential function because the variable is in the exponent, right? Okay. So let's talk about the domain. We said that the domain is always all real numbers. We can use any number to represent our variable term x. But what's happening to this range? Is this range ever going to go into the negatives? Is this ever going to be negative? No. So this is all y that are greater than 0. Y is greater than 0. Okay. So when you look at this function, as x gets bigger, what happens to y? as x gets bigger, y approaches positive infinity. Okay. For all x's that are greater than 0, y just keeps getting bigger and bigger and bigger, right? As x gets smaller, when x gets smaller, y approaches 0. It's never going to go negative. It's just going to get closer and closer and closer to 0. It's never going to touch 0, but it's going to get really, 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 really close. When you look at your second example, the domain, still all real numbers. Okay, all real numbers. The range, this is going to get really close to crossing the positive into the positives on the y-axis, like crossing over that, but it never is. So the range is just going to be all y values that are less than 0. It's never going to get to positive numbers, and it's never going to equal 0. Let's talk about the end behavior. As x gets bigger, so for all x greater than 0, what happens to y? Where is y going? As x gets bigger, as I move across this x-axis, what happens to y? Yeah, it approaches negative infinity. It gets really, really, really small. Okay. And as x gets smaller, y approaches 0. We talked about end behavior. And looking at a graph. Okay. So those are exponential growth or decay. This one is an example of decay, right? This one is an example of decay. This is also growth and decay. I'm not going to refill those out. We know this. So let's talk about how to graph this. So let's look at this. Remember that we're graphing this function y equals a times b to the power of x. And we said that a is where we cross the y-axis. So I'm going to plot that point first. 0, 1, 2, 3. This is a. Okay. So b is my growth factor. B is 2. So if I let x equal 0, when x equals 0, anything to the 0 power is 1, 2 to the 0 power is 1, 3 times 1 is 3. That's why when x is 0, y is 3. But if x equals 1, I have 2 to the first power, which is 2. So I'm taking this and multiplying it by 2. So when x is 1, I'm at 6. Y equals 6. When x is 2, when x equals 2, well, 2 squared is 4. Y equals 12. Do you see what we're doing to our value each time? Let me fill out another one. I'm just going to make a table really fast. X and Y. So when x is 1, y is 6. When x is 2, y is 12. When x is 3, y is going to be 24. When x is 4, y is going to be 48. What do you think is going to happen when x is 5? Yeah, 96. What am I doing each time, Hayden? Yeah, I'm doubling or taking every number and multiplying by 2. Take the one before it and multiply it by 2. So this is going to look like this. Your graph is going to go like this, right? It's going to just go like this and it goes off the charts, but that's what your graph looks like. The domain, all real numbers. The range, y is always going to be greater than 0. And I'm just going to put as x approaches infinity, positive infinity, y approaches positive infinity. Yeah. Yes, for exponential functions, it's always all real numbers. Yes, sir. The only time your domain is not going to be all real numbers is like when you're dealing with like square root functions, because you can't take the square root of a negative number, or when you're dealing with logarithms and things like that. Okay, that's a good question. But when we talk about linear functions and quadratic functions or exponentials, it's always going to be all real numbers. With the exception of if it's a real world problem, Peyton, like, and we're talking about time, right? And X is really the value of time. You can't have negative 80 minutes, right? So unless it's a real world, yes, good question. Are we still writing this down? So example 2 is decay because my growth factor is less than 1. So everything is getting smaller. So we're going to, instead of multiplying by 2 here, we're going to do what? Divide by 2. So if I think about my table of values, A is negative 2. So when X is 0, Y is going to begin at negative 2. But when X is 1, I'm going to take this and divide by 2. What is half of negative 2? Yes, it's negative 1. And when X is 2, what is half of negative 1? Yeah, or negative 1/2. And when X is 3, what is half of a half? Negative 1/4. And when X is 4, what is half of a fourth? Yeah. Do you guys see what's happening? So if I were to graph this, I'm going to begin at negative 2, and then X is going to go to negative 1, and then negative 1/2, and then 1/4. And it's going to get really, really, really close to 0, but it's never going to equal 0. It's never going to equal 0. Okay. If I let X equal negative 1, if I let X equal negative 1, this gives me negative 2 times 1/2 to the negative 1 power. What happens to that 1/2 to the negative 1 power? What does it really become? It becomes a 2. So I get negative 2 times 2, which is negative 4. So I just took this number and I worked backwards. Instead of dividing by 2, I multiplied it by 2. So negative 1, negative 4. Negative 1, 2, 3, 4. So at negative 2, I'm going to equal negative 8. So my graph is going to go like this. Domain, all real numbers. Range, Y is always going to be less than 0. As X gets bigger, Y gets closer to 0. As X gets smaller, Y gets smaller. Tell me when you're ready. Then we talked about the last thing that we did was we did percent increase or decrease, right? We talked about percent increase or decrease, and we talked about compound interest. Okay. So exponential growth and decay, well, there's another formula for that. And it's like this, where here is your initial amount. This is your beginning value. You take 1 plus your rate, which is usually a percent. So like 2% is the same thing as 0.02. That would be your rate. If it was a 10% decline, it's going to be a negative 0.1. So if it's decaying, and then we use the number of periods. T is usually like in time, usually in years, but it could be in minutes or hours, like if it's bacteria growth or things like that. So we said that the growth factor is either positive or negative. If it's negative, it's showing decay. And it's used when situations increase by a factor amount. So here is an example. You start with $1,000. This is your beginning amount. Okay. At the end of 6th grade, you put it in an account at the end of 6th grade. It pays you 5% interest. So your rate is 5%. Turned into a decimal is what? 0.05. Yeah, remember you move the decimal 2 places to the left. How much money will you have after 6 years? This is your T. T equals 6. So let's look. Y equals 1,000. That's our A value, times 1 plus our percent growth, which is 0.05. And for how many years? 6 years. So I'm going to simplify this. Well, that means that Y equals 1,000 times 1.05 to the power of 6. I'm going to put that into my calculator and see how much money I have. So 1,000 times 1.05 to the power of 6. And after 6 years, I have $1,340. And if I round up, 10 cents. So it says define your variables. Well, we already did this. Like we determined that it's growth. We defined our variables as we read the problem. We told you what A is, what R is, and what T is. Use the model to solve the problem. We already did. Done. Do you guys remember doing stuff like this? And I gave you that little foldable that had Y equals A times B to the power of X. And then we did examples on the inside. I don't know if you still have those notes or not, but you guys did really well with exponential growth and decay. And you did really well with compound interest. Your compound interest notes were your doodle notes. Okay. So we're going to do another one. Let me know if you're ready. Okay. So for this one, it says the initial value of a car is $25,000. The value of the car decays, meaning it's like depreciating, it's losing value each year. Estimate the value of the car after 5 years. So we're using this model, Y equals A times 1 plus R to the power of T. Let's identify all of these things that I've boxed in. Let's say what variables they represent. What is A? Yeah.
Is it 1 plus R?
It's 1 plus R to the power of T. Yep. So A is 25,000. Remember, that's your initial amount. Initial amount. So my car was originally worth $25,000. What is my rate? Yeah, it's negative 15% because it's a decay. And yes, Hayden said negative 0.15. Negative 0.15. If it's decay, we're going to lose money, right? So we have to shrink it. What is my time? Yeah, 5 years. Okay. So, So Y equals A, which is 25,000 times 1 minus 0.15, right? Because it's a negative rate, all to the power of 5. Well, when I simplify that, that's just the same thing as saying Y equals 25,000 to the power of times 0.85 to the power of 5. 25,000 times 0.85 to the power of 5. So what is my car worth after 5 years? Yeah, $11,092.63. That's bogus. That's crazy. Your car is losing almost $3,000 in value each year. So does that make sense? I'm going to write a little note over here. Remember, decay makes the rate negative. So we want to shrink the amount of money. We don't want to increase it. We want to shrink it, right? Decay means we're shrinking the value. Two more examples. I know you guys. If it makes you feel any better, we're not doing a lesson tomorrow, okay? We're not doing a lesson tomorrow. Are we ready to go on? Okay. That doesn't mean don't come to school tomorrow. It just means we're not doing a lesson. Okay. So solving exponential equations. This was the last thing that we did with exponents. And I will tell you that we struggled with this. Really, really, really struggled. So I think that I can maybe think of a better way to do this, but I'm not really sure. So here's what I want you to think about. This, we're trying to solve for x, right? So here's what I want you to think about. What number to the power of 3 is equal to 1,000? That's what this is really asking you. So in your calculator, you have a math button. You have a math button. And if you click on the math button on your calculator, and then you choose number 4, it gives you this symbol. Gives you the cube root symbol. So if we want to, remember how we like unsquare stuff, right? Because if I had x squared equals 64, you guys would just take the square root of both sides. Well, I can't take the square root of it because it's not a square, it's a cube. But I can take the cube root of both sides. You just need to know where that button is in your calculator. Okay. What'd you get, Madeline? Yeah. Yes, it's 10. When you take the cube root of 1,000, you get 10. So x equals 10. Very good. So let's look at this one. 25 is the same thing as 5 to what power? Well, if you don't know, what is 5 to the first power? That equals 5. What is 5 to the second power? It's 25. So x equals 2. So I want you to think about how we did this. So when we learned this lesson and we started to come to numbers that we're not real familiar with, like this, we were like, what's happening here? So here's what I want you to think about. I want you to think about writing this number as a power of something. Let's see. So x to the negative 2 equals. So let's see. I know that 121 is the same thing. This equals 11 squared. 121 is the same thing as 11 squared. How can I rewrite this so that it's just the number 11? What can I do to that fraction? How do I move that so that the number is 11 instead of 1 over 11? Yes, make the exponent negative. It's the same thing as 11 to the negative 2 power. So what is the value of x? What is the value of x? Yeah, x equals 11. X equals 11. Do you see that? So for this one right here, you have to think about 1/3 to some power is the same thing as, Let's figure out a way to write 127th as a power of 1 over 3. So 3 to what power equals 27? Well, what's 3 to the first power? 3. Okay, what's 3 to the second power? 9. What's 3 to the third power? So this is the same thing as 3 to the third. Well, what is 1 to the third power? 1. So what can I say that my exponent is? What is the value of x? Look at what I did to this. I just took it and put it here and here. What are the values there and there? They're exactly the same. It's 3. Okay. And we did not do this remainder. You don't do that. We did not do that at all. So you can just scribble that out. We did not do remainders. But I am going to try to do this right here. So this is saying what number to the fourth power equals 81. So let's see. 81 is the same thing as 9 times 9, which equals 9 squared. But 9 is the same thing as 3 times 3, which is 3 times 3, which equals 3 to the fourth power. So what is x? What number did I raise to the fourth power to get to 81? 3. You guys try number 2 and number 4. I'm going to freeze the screen. You try 2 and 4. Pardon me? 2 and 4. Are we ready to see them? So for the first one, I just wrote out 4 times 4 times 4 is 64. That means I took 4 to the third power. So x is 3. If you could just start plugging numbers into your calculator. 4 to the first, 4 to the second, 4 to the third until you get up to 64. Just start raising 4 to a power. For number 4, I thought about it differently. The first thing I did is I was like, okay, what number can I multiply together to get 32? That's a power of 2. So I started with 1/2 times 1/2 times 1/2 times 1/2 times 1/2, because I know that 2 to the fifth is 32. So 2 times 2 is 4, times 2 more is 8, times 2 more is 16, times 2 more is 32. But I know that 1/2 is the same thing as 2 to the negative 1 power. And if all of the bases are the same, you add your exponents. Negative 1 plus negative 1 plus negative 1 plus negative 1 plus negative 1 is negative 5. So 2 to the negative fifth is 1 over 32, which means x is negative 5. Which brings you back to number 3, which means here that x is what? 2. Because if x to the negative fifth if, like you see here, you were finding the base, here you were finding the power. Okay,